This is lecture 2.5 for Psych 440, Measurement. This lecture is a little bit longer and a little bit more technical than some of the others in this module. If you've taken a course in psychological measurement, some of this will be review. If you haven't, it's very important for understanding the way that we use tests in IO psychology. We use psychological tests and measures in a number of scenarios. We use them to select employees. We use them to measure things like employee engagement. So it's very important to understand how it is that we measure things and to be able to interpret measurement terms. Now, if you've studied psychology for a while, you've probably noticed that where fields like biology use Latin for their technical terms, in psychology we like to take perfectly ordinary words that already have perfectly good meanings and assign them much more specific meanings. So in casual conversation, it's not uncommon to hear someone say, "Oh yeah, your feelings are totally valid." The use of valid that way is actually very different from what we mean when we say a test has validity evidence or a test has been validated. If you're talking with professionals in the field, if you're talking with people who are knowledgeable, and you make a claim that a test is valid, that implies a specific technical sense of validity with some specific evidence to back it up, not just the casual sense of, yeah, that seems reasonable to me. So if you're working with other professionals in the area of IO, and you're using these terms loosely or incorrectly, then you're likely to be sending the wrong messages. You might actually be giving people misinformation. So it is actually very important to pay attention to the specific meanings of these terms and be able to use them in the way that professionals in the field use them. So we'll start there, and then we're going to talk about the main problem that we're concerned with in psychological measurement. We don't, at this point, we may not ever, have a way to go in and scan people's brains and get a precise measurement of their level of cognitive ability or conscientiousness or job satisfaction. We have to use psychological testing principles to come up with our best estimate. That means our best estimate is going to have some error in it, but there are steps we can take to reduce and then try to account for the error that we do have. As a quick preview, if you've ever wondered why it is that psychological tests and surveys ask basically the same question in different ways, you're going to find out. When we quantify the amount of error that we have in a test, we call that reliability. And you may have come across reliability in other courses. You might be aware that there are different kinds of reliability. And we'll talk about 4 major kinds. It's very important to know that these are not interchangeable. They're not just different ways of calculating the same thing, but every type of every type of reliability addresses a different kind of error. So I want you to be able to match them up to know what kind of reliability is most appropriate if you're most concerned about a particular source of error. And then finally, we'll wrap up by talking about validity. There is a slightly more complex, more sophisticated modern view of validity than the one that's presented in your textbook. But the one that's presented in your textbook, it will do for now. I just want you to be aware there's a little bit more out there. But historically, we've made this distinction between 3 major kinds of validity evidence. We can talk about evidence related to the content of a test, criterion-related evidence, and construct-related evidence. And you'll see these terms used quite a bit if you're reading the psychology research literature, so it's important to know what they mean and why each of these things is important. So let's get started with the terminology. First of all, it's helpful, I think, to have a definition for measurement. This is a pretty well-established definition that's been out there for quite some time. The assignment of numbers to objects or events using rules in such a way as to represent specified attributes of the objects. Now, some of those terms are a little broad, a little general. An attribute here is going to be any characteristic on which people vary. We're not interested in measuring things on which people are all the same. It would not be particularly useful to develop a psychological test that could tell you whether someone was breathing or not. It might be more interesting to figure out how fast someone was breathing, or how steady or consistent their breathing was, but if people are all the same, there's nothing to measure. So measurement is most relevant when we're concerned with characteristics on which people could vary. These could be physical characteristics like height. Most of the time we're concerned with psychological characteristics. These could be long-term, long-lasting characteristics like intelligence or personality. They could be short-term characteristics like mood or flow, deep engagement on a particular task. What we're trying to do here, you'll also often hear the term construct. A construct is an attribute that's not directly observable. So height here would be an attribute. We could see that directly, we could observe it, we don't have to make a lot of inferences there. Something like intelligence or extroversion, that's an abstraction. We have to infer somebody's level of intelligence or infer their level of extroversion from their behavior, whether that's their self-descriptions of their own behavior or our direct observations of them. So we're interested in measuring attributes. Most of the time we're interested in measuring the subset of attributes that are abstract and are constructs. So I could have maybe nested this bullet under this one. All constructs are attributes, but not all attributes are constructs. In general, what we're trying to do in psychological measurement is take things that are abstract and intangible and define them in terms of behaviors that we can observe. Sometimes those behaviors are complex, like taking a driving test. Sometimes they're as simple as filling in a bunch of bubbles on a Scantron test. Important in IO psychology because we use psychological measures of varying quality to make decisions about people. We use measurements, whether it looks like a formal paper and pencil test or not, to decide who we're going to hire. We very often use them to decide who gets promotions, who gets bonuses or raises. We use them to recommend changes to organizational processes. So if I go into an organization and I conduct an employee engagement survey and I recommend that the organization change up their management structure so that employees have more autonomy and more responsibility, before the organization commits to that expensive and difficult intervention, they'd like to be confident that I was really right about their employees' level of engagement. It matters in IO because we're making decisions that affect people's lives. So we need to have some evidence, some good reason to believe that our measures are accurate and that they're fair to everyone involved. The challenge in getting our measures to be accurate and fair is measurement error. When we're talking about constructs, remember, abstract attributes, no single item can perfectly measure an abstract construct. In classical test theory or psychometrics, we use this very simple model that says when a person is responding to an item on a test or a survey, there are two things that go into that response, or two large categories of things. Their observed response is a function of their true level of the thing that we're trying to measure, plus or minus some amount of measurement error. Now, for any single item, we can't solve this equation. If I've just got one observed response, I can't separate out how much of that single item is true construct and how much of it is error. But in this model, we define error as everything that's not true score. That means it's random. And as we have several items across all of those responses, our measurement errors should cancel one another out. That's why, when we're trying to get at something, we're going to ask similar things in slightly different ways. Let me give you an example. Say that I would like to measure the construct of liking for pizza. Now, imagine that on the theoretical possible continuum of liking for pizza, your true score is right about a 4 on a 5-point scale. You like pizza quite a bit, but it's not like the best thing ever. So your true score for liking of pizza is about a 4. Now I ask you to rate a set of attitude items about your liking for pizza. I ask you to rate those on a scale from strongly disagree to strongly agree. Let's put out some items there. If you say item number 1 is, I like pizza. Well, now you look at this item, you say, well, yeah, of course I like pizza. Your true level of liking pizza is a 4. You say, of course, naturally, everybody likes pizza. Why wouldn't I like pizza? So you reply with a 5. You strongly agree. Well, now the measurement error here means that your response isn't a perfect reflection of your liking for pizza. But you go on and you answer some more of the other items. Pizza is my favorite food. Well, no, it's not my favorite. I like it, but it's definitely not my favorite. I think I'm going to pick a 3 for that one. Well, now here, your response to this item is off. It's distorted from your true liking, but in the other direction. If I used either one of these items by itself, I would have an inaccurate estimate of your liking for pizza. But we'll throw one more item into the mix. I am always up for a pizza. Well, I'm usually up for pizza, but not always, so I'm going to say 4 on this one. That one ends up being right on. If I average across these items, now I've come up with a pretty reasonable estimate of your true score. Now, it's not always this straightforward. The errors aren't always perfectly balanced. Sometimes we need a lot more than 3 items to come to what we feel is a pretty good estimate. But hopefully this shows you how measurement error works. Any single item depends a little bit on the way you individually interpret those items and your own particular response tendencies. But across a large set of items, we should get closer to your true score. The conceptual opposite of measurement error is reliability. Sometimes you'll hear people define reliability as the consistency of a measure. Your textbook gives what I think is a much better definition. It's the dependability of a measure. Consistency is actually a more specific form of reliability. What we mean when we say a test has good reliability is usually that it's precise. The technical definition of reliability is how much of the total variance in our test scores is real compared to how much of it is error. Naturally, we want tests that are mostly true variance, where most of our variance is not due to error. So reliability gives us a way to estimate and quantify just how much measurement error do we have in this test. When we have good reliability, then we feel confident that we're really capturing something about the person. Not just the setting, not just the day we happen to administer the measure, not just chance, but something real about the person. It doesn't necessarily tell us what we're measuring. So reliability doesn't tell us that we're measuring what we set out to measure. We're measuring something about the person. We don't know what that something is until we look at validity evidence, which is coming up in just a few more slides. When we have poor reliability, basically it means we have more noise than we have signal. And we don't want to trust the scores that we get from a measure with poor reliability. If we have a measure with poor reliability, reliability shrinks the correlations we're able to find between our measure and other variables. So if we're using a measure with poor reliability, we're going to make the wrong decisions about people. If we're using it in a research context, we're going to make it harder to find relationships among constructs that are really there. So reliability is the absolute minimum standard for a measure. If you cannot show that your measure has good reliability, you got nothing. You don't want to make any decisions based on that measure. It's not going to be useful for exploring research questions. You might as well not have used it in the first place. Now, I mentioned before that we have different types of reliability. Each of these types of reliability addresses a different kind of error. And I'll kind of list them for you, and then I'll talk a little bit more about what kinds of error they help us deal with. One of the easiest types of reliability to understand is test-retest reliability. This tells you how stable your test is across time. It controls for measurement error due to time, or things that fluctuate over time, like your mood or whether you ate a good breakfast that day. If you're concerned about measuring something in a way that's not going to be influenced by those temporary factors, you might want to calculate your test-retest reliability. A similar idea, but it gets at a different kind of error, is parallel forms reliability. We use parallel forms reliability when we don't want to give the same test twice. If I gave you a measure of conscientiousness today and I gave it to you again tomorrow, you're probably going to remember your answers across those two sets of questions. If I gave the certified public accountant exam to a group of test takers, and then some of them didn't pass, and they came back 3 weeks later and took the same test, they would probably have some consistency in their scores just by remembering the same answers. That's not what we want. So sometimes we want to see, can I create two different versions of the same test? If I create two versions, then it shouldn't matter which one you get. That's parallel forms reliability, is when I can use two versions of the test interchangeably. We're not always concerned with paper and pencil tests. Sometimes we're concerned with measurements based on behavioral observation or ratings. You may remember from your research methods class that if you're making observational ratings, you really want to have two raters, and you want to be able to show that they agree. That's inter-rater reliability. Does it matter which rater you have? And then finally, all three of these types of reliability are assessed in the same way. We give the test either same test on two occasions, two versions, or two raters, and we're going to correlate the scores across those things. So test-retest is just the correlation between time 1 and time 2. Parallel forms reliability is just the correlation between test 1 and test 2. Inter-rater reliability is the correlation between rater 1 and rater 2. What we want to see is that they come out pretty much in the same rank order every time. So this here is a visual example of good reliability. Across our time points or our tests or our raters, we're giving people very similar scores. They're coming out in pretty much the same rank order across both measurements. This would be an example of what we don't want to see. Really big differences across time points or tests or raters. People come out in a totally different rank order over here than they did over here. Up here, we'd say, well, it doesn't really make a difference to your test score whether you took it at time 1 or time 2, test 1 or test 2, whether you were observed by rater 1 or rater 2. Down here, in this example of poor reliability, this makes a huge difference. So there would be a low correlation in this scenario, there would be a high correlation in this scenario. So those three types of reliability all get calculated the same way, but they're concerned with different sources of error. Is the source of error time point? Is it the particular version of the test? Or is it the rater? You can see that not all of these are going to be applicable in all situations. If you don't have raters, there's no need to test inter-rater reliability. If you're only creating one form of the test, there's not any advantage to parallel forms. There's one type of reliability that is almost always going to be relevant, and that's called internal consistency reliability. The easiest way to understand internal consistency reliability is with its simplest calculation. If you have a test with 10 items on it, and you want to know how much error is being introduced by differences in my items. Some of my items are better than others. Would I get the same results if I had asked the questions in a slightly different way? Well, you can estimate that by taking your test and splitting it in half. Randomly, systematically, there are lots of ways to do this. But if your scores on one half of the test are pretty highly correlated with your scores on the other half of the test, then you can feel pretty good that all of those items are measuring the same thing. That it doesn't matter exactly which items you ask, but they're all going to point you in the same direction. Split half reliability used to be very common. It's very easy to calculate, but the more modern version, the thing you'll see most people use most of the time, is something called Cronbach's alpha. You don't calculate alpha by finding all the possible split half correlations and averaging them, but that's what it works out to. So you can see that this might vary depending on exactly how you split up those items. Alpha is going to give you your very best estimate. If you split it every possible set of ways, what would your reliability coefficient be? So although this isn't calculated as a correlation, it's interpreted on the same metric. All of these, we're looking for large correlations or large alphas. In particular, we want to see those being above 0.7. Now, there should be questions showing up for you over on your right-hand side. What does it mean to say that a test is valid? When we say that our test is valid, we're implying that we have specific empirical evidence that our test means what we think it means, that our scores can be interpreted in the way that we want to interpret them. It's not just a value judgment. It's not, yeah, that seems like a pretty good idea. It's something for which we need to have concrete evidence. Now, earlier in the module, we talked about internal and external validity. Those are properties of studies or experiments. Internal and external validity don't apply to measures. We have more specific terms to describe the validity of tests and measures. Your textbook gives a definition of validity that says it's the extent to which a test measures the underlying construct that it was intended to measure. That's a pretty good definition, but in the modern view of validity, we get a little bit more specific with it. We say validity is the degree to which it's reasonable to say that we can make the inferences we want to make from our test scores. And that's kind of a subtle distinction. It's okay if you just want to stick with the definition from your textbook, but what it's acknowledging here is that a test may have great validity evidence for one purpose, but not necessarily for another. So, for example, you might be familiar with the Minnesota Multiphasic Personality Inventory. It's a very, very famous psychological test. It has some great validity evidence for diagnosing things like schizophrenia and depression. According to this definition, it's a valid test. However, the way that the MMPI was developed, it's not really meant to predict job performance. It's not designed to measure well in the normal range. It's designed to measure people who are out at the extremes. And so, although you can say it's a validated test, it does measure the underlying constructs that it's intended to measure. It does a great job at some of those things. It's not necessarily reasonable to interpret someone's scores on the MMPI as evidence of their suitability for a particular job. So in the modern view of validity, we don't really talk about a test as being either valid or not valid. We say, well, what are we going to use it for? How do we want to interpret those test scores? Are those inferences valid? Are they appropriate? What this means is that we don't have a single statistic that we can use to say, yes, this test is valid, no, this test is not. In fact, in the modern view of validity, when we talk about validity, we use a courtroom metaphor. And the idea is that you're accumulating lots of evidence. You want to show that you have lots of different types of evidence that all supports the interpretations you want to make from your test score. In particular, we're going to spend a lot of time in this course talking about two kinds that come up as particularly relevant for I/O, and that's content-related validity evidence and criterion-related validity evidence. Content validity is the degree to which the test covers a representative sample of the quality being assessed, or the attribute or the construct being assessed. Now, this seems reasonable at first glance, but when you think about it, well, how do you get a representative sample of a construct? We don't have, there exists, as far as I know, there's no item vault that has all the possible items we could ever ask about cognitive ability or personality. We have to write them. So when we talk about content validity, what we're really saying is, how do we know that we're measuring all of the thing that we want to measure, we're not leaving anything out, and we're not including things that aren't what we want to measure? So if I'm measuring math knowledge, I would want to sit down and think about what are all the areas of mathematics that are relevant in this situation. I would want addition and subtraction and geometry and trigonometry maybe. It wouldn't be appropriate, you wouldn't buy it, if I gave you a test that I said was general math knowledge and all of the items were about fractions. You'd have a problem with that. That's not really representing the whole construct. At the same time, I want to make sure that my test doesn't have extra stuff in it that doesn't belong there. If I give you a test that I say is supposed to measure your math knowledge, but it's really good, what it's really driven by is your knowledge of test-taking tricks and tips, well, then I'm measuring the wrong thing. And it's not appropriate for me to conclude that that test really means something about your math knowledge. In I/O psychology, when we talk about content validity, we usually mean job relatedness. We're usually talking about tests in relation to job performance. So we want to know that our tests include things relevant to all the important parts of the job, and that they don't include things that are not relevant to the job. So when we talk about content validity, we're focused not on any statistics about the items, or not on very many statistics about the items, but on what's the content? What are those items asking about? Is it relevant? Is it appropriate? Is it related to the job? The other major type of validity evidence that we're concerned with in I/O is criterion-related validity. We're often interested in using tests to predict things. We talked earlier in the module about outcomes and dependent variables and how prediction is often a really important goal of science. When we talk about criterion-related validity, sometimes we differentiate between concurrent validity and predictive validity. We'll talk more about the difference between those later in the course, but for right now, the difference is, when are we measuring the outcome? Concurrent validity means we measured it currently, we measured them both at the same time. Predictive validity usually means that we gave the test now and we waited to measure the outcome in the future, so that we could be really confident that our test scores really are going to tell us what's going to happen down the road. For many I/O psychologists, criterion-related validity ends up being the most important type of validity. If you are using a test in a selection context, this is the most important type of validity to show. The others are important as well, but if you hear an I/O psychologist talking about something as a valid predictor, they usually mean criterion-related validity evidence. This is going to be the key thing in applied contexts. Finally, just one more term for you. On the research side in particular, we're also concerned with construct validity evidence. This is the type of validity that really best gets at, are we measuring what we think we're measuring? So construct validity we can define as, does our measure relate to other constructs and other measures in the way that we would theoretically predict that it ought to? So we might predict that a measure of one construct, like conscientiousness, should be highly related to other people's measures of conscientiousness, or it should be related to similar things like detail orientation. We call these strong relationships, these things that we expect should be strong relationships, convergent validity evidence. At the same time, we want to be confident that our measure is not measuring things that we didn't intend it to measure, that it's not just a function of the mood the person was in at the time they took our test. It's not some other construct that's similar to ours, but that wasn't the one we set out to measure. So when we're testing, making sure that our test doesn't measure things it shouldn't measure, we call that discriminant validity evidence. Alright, so this lecture was a lot of technical terms and concepts. They are all things that will come back again later in the course, so if you're feeling a little fuzzy on some of the details, certainly ask questions, certainly look back at your textbook, but know that we will get into more depth on many of these topics a little bit later. For right now, I want you to know what these terms mean and be able to distinguish between them. Have a sense of when each one is going to be appropriate. In the next module, we're going to move on and start talking about job analysis, which is the way IO psychologists answer the question, well, what exactly is it that people do here?